Okay, so moving on to the uncertainty. Obviously, a deterministic model, if you compare one run to what happens in observations in detail, you're going to say, man, this is terrible. But you can still, if you fuzzy your eyes a little bit and don't take the details too literally, it can be useful. And so the same thing is, if you have an ensemble of these runs, you can get some utility out of them. Obviously, the issues are smaller scale processes. If you don't get things right initially, you can go way, way off track as well. We don't really know the atmospheric state, as I mentioned before. And certainly predicting individual storms, 12 or more hours in advance is very difficult. And convective storms are very unpredictable in general. So this just stresses that, you can have models initialized at the same time. They all may seem plausible, but, what's the real solution? So using an ensemble approach to help understand the uncertainty and location, timing, mode, intensity, and that can be useful. So convection-allowing ensembles, I'm talking about roughly 3 to 4 kilometer grid spacing. Almost all now we're moving to 3 kilometer. We had been at 4 for some time. Give us some uncertainty information, like I mentioned, especially when we're talking about outlook to watt scale. And as we move to updating forecasts, you guys maybe heard of the Facets Initiative, obviously Warn on Forecast. As we move to updating things and having higher temporal resolution, obviously convection-allowing ensembles is going to help us out. Traditional forecasting, ingredients-based, you can come up with rough timelines, but we're going to get a lot more explicit timing information from convection-allowing ensembles. So history of these basically goes back to the hazardous weather testbed I referenced that earlier, HWT, that CAPS here at OU has run since 2007, a convection-allowing ensemble, starting with 10 members in 2007, and they went up all the way up to 50 members in 2011 and have since backed down a little bit based on some of our findings I'll talk about. And again, we look at storm attributes, the hourly maximum fields. And I'll reference the storm scale ensemble of opportunity that we generated at SPC. It's basically EMC started running all these different CAMs, and the forecaster said, I can't look at all of these. And so it was essentially a way to just summarize the information. That was the initial intent, and I'll show you what came of that. So we do some processing of the storm attribute fields. As I mentioned before, the forecasters really like the temporal aggregation of these hourly max fields, so that's how we display it. And also, we use a spatial maxima or neighborhood approach. We use 40 kilometers because our probabilistic definitions at SPC are within 25 miles, so that's roughly equivalent. And so we can get probabilities that are relative to our outlooks. So Amy Harless was a grad student here, and she did some work on looking at, what's the appropriate neighborhood and so forth. This just shows that using a variety of different neighborhoods. This is at the grid point. You can't see anything because it's basically just low probabilities at the grid point. As you increase the radius, this is 10 miles, 25 miles, you see that your probabilities go up. Obviously, it's very difficult to get grid to grid point matches, for different convection-allowing model runs. It's just not that things aren't that predictable. So if you allow for some spatial uncertainty, you can get probabilities that are somewhat meaningful. And then if you apply it as you go from left to right here, you're sort of using a two-dimensional Gaussian smoother. Just again, there's a lot of uncertainty in this forecast. We can account for that with Gaussian smoothing. So there's what you can color code by member, sort of your traditional spaghetti or paintball plot. And here's your probability at the grid point there. You can see low probabilities. There's a little area in Tennessee that does get up to 50%, but most of them are 20% or less. If you apply a neighborhood, you can see the circular nature of the neighborhoods. You get higher probabilities, and then it's more aesthetically pleasing to look at a probabilistic field like that. So that's how we generally view convection-allowing ensemble outputs. there's a multi-hour maximum from the ensemble on April 27th, 2011, and then the probabilities from that. So a lot of times, you know, using this approach, you can encompass a majority of severe weather on active days. So I want to talk a little bit about some of the results that we've seen on convection-allowing ensembles in the hazardous weather test bed. I'm not going to hit all the details of this, but just I had mentioned the SSEO before. It's a 7-member. It's one of the things to keep in mind. It's multi-model, so it has ARW, NMMB, and an old WRF NMM run in there. Where, like, I'll refer to the CAPS storm scale ensemble forecast system. It's a more advanced, uses multi-initial conditions with Schreff perturbations. It's basically a formally designed ensemble. The Air Force used a global forecast to initialize their model. And you guys have probably heard of the NCAR ensemble, 3-kilometer grid spacing. They do ensemble data assimilation on a 15-kilometer grid, 50 members, and then they downscale 10 members to 3 kilometers and run launch forecasts from those coarser runs. So one of the surprising things we saw in 2011, like I said before, the SSCO we designed just as a way to summarize information from the CAMs. But when we started comparing it to these formally designed ensembles, it actually performed better. So this is just comparing storm reports to UH neighborhood probabilities. And basically scored better than any of the, even a 24-member ensemble that CAPS produced. It's outperformed. And these are just some subjective results looking at QPF forecasts. Generally, the SSCO was comparing favorably or even doing better than some of these formally designed ensembles, and that was very surprising. We didn't expect much from it when we designed it. This is 2012. We saw basically similar things. We looked at reflectivity forecasts, UH forecasts, and it did pretty well. 2013, the CAP system was improved, and so they're roughly on the same field. You can see the dashed red line here is this ensemble had radar data assimilation, so you can see the positive impact of getting storms right early on and then sort of evening out over time. 2015, we had kind of this look at all the ensembles that are being run by different groups at this point. We had NSSL, the Air Force, NCAR, and then CAPS here at OU. And so we had several different convection-allowing ensembles. And I think the takeaway that we got at that point, just looking at fraction skill score for reflectivity, probabilistic reflectivity forecast, they're all doing about the same. It's like no matter how you design it, it doesn't really make that much difference. So it's a little disheartening that if we design something formally, we hope it's going to do better than something you just throw together, sort of. But I think it tells us our understanding state of the science on it at this point. I'm going to skip that, go to a little bit more about configuration. So the question is, why would this basically poor man's ensemble, the SSCO, perform as well as more formally designed? So some of the aspects, single model versus multi-model. The SSCO is multi-model, obviously, as I mentioned, and a lot of these other ensembles are single model. As I said, with the convective parameterization models like the Schreff, that's one of the benefits, because you get this clustering, and like we saw in the global ensemble, if you have a systematic bias, say in PBL scheme over mixing, you don't have anything to adjust or account for that. This just shows basically that it's good to have a variety of models with different biases, and we've seen that in other fields as well. This is for reflectivity. The NISL WRF, which is favored by SPC forecasters, actually is quite an over-forecaster. It generally has a high bias in reflectivity, but they prefer it. We have, obviously, it's better to not miss a big severe event than to under-forecast it. So some of the other members of the SSCO are more of under-forecasting bias. Some of the work that Adam Clark at NSSL has done looking at convection-allowing ensembles compared to convective parameterized ensembles. For the convection-allowing scale, he found that for QPF, at least, around beyond 9 members, your skill, your point of diminishing returns occurs. Basically, you're just not getting enough enhancement in the skill beyond adding more members to that. And then initial conditions. I think having initial condition diversity is important. In fact, that's how that's the only diversity in some of the ensembles that we've looked at convection-allowing scale. But I think still getting the right scale of perturbations on these initial conditions is really something that needs work. And then having physics diversity, we talked about how complicated, complex the physics interactions are. And so having some diversity in that so you don't get too much systematic bias, I think, is important as well. So our effort this past year was to try to have more controlled experiments. We saw in 2015 several different groups just producing their own ensembles. The problem with that is we can't really say why one's better than the other because it's not a controlled experiment. So we designed this community leveraged unified ensemble, or the CLUE, in 2016 to help us out. And so we had different groups from the community help us out: NSSL, GSD, NCAR, so a lot of the major convection-allowing model experts, and they all agreed to same specs. We had these different experiments. Too many details to go into, but I'll show some results quickly on some of that. So the idea here is that these experiments will help inform the next, or the first operational convection-allowing ensemble and the versions that come down the line. So one thing that I've hit on already, the SSEO basically was established as sort of the reference that all ensembles should try to meet or exceed. And so I think just mention one thing about this is a reliability diagram. You want to be close to this diagonal. Notice that all these forecasts, if you fall below the diagonal, you're over forecasting, so you're overconfident. You don't have enough spread in the ensemble. The SSEO, or the blue dot's a little hard to see, but it has the most spread, basically. It's the closest to reliable in terms of probabilities. The others actually fall below the no skill line, so there is some utility certainly in their forecasts, but in terms of, you know, reliable probabilistic forecasts, that's where we really struggle at these scales. Adam did some analysis looking at having a multiple core ensemble. That's this bottom plot compared to the NMB ensemble and the ARW only ensemble. There is some advantage, I think, to having a multi-core ensemble at this point. Radar data assimilation obviously has an impact to solid line out. We found about 15 hours into the forecast, it gave improved fraction skill score for reflectivity. And then the size of the ensemble. This was pretty interesting, and Adam referenced it in an earlier paper where if the lightest blue line is only 2 members, and if you double that to 4 and then go to 6, 10, and 20, you do improve the score, but it's very limited. So again, it's this point of diminishing returns. It's very expensive to run more members, but you're not getting a whole lot in return. So this is my last slide. The multiple core strategy at this point, I think, is still worth pursuing. The problem is EMC is on a quest to unify all modeling, which is noble, but at the same time, if it's not going to lead to improved forecasts, that's an issue. There is maintenance cost involved with having multiple cores and maintaining them, so it's certainly understandable. Not surprisingly, radar data assimilation has a positive impact. We found it a little longer for just deterministic runs. In a probabilistic sense, this radar data assimilation lasts about 15 hours from what we saw last spring. We also saw that the ensembles are very underdispersive, so it leads to over-forecasts, overconfidence. And it's just because we don't really know how to best perturb the ensemble. That's really what it comes down to. A lot of these ensembles use various methods, but in general, we just can't get enough spread to do it. So a lot of work, I think, needs to go into how to best design a convection-allowing ensemble in terms of perturbations, multiple physics. Do we need a multiple core? Will we ever get enough spread from a single core to work at these scales, especially as you go out to day 1, 12 to 24 hour to 36-hour forecasts?